So this will be my third and final video in a sequence exhibiting how to find asymptotics from generating functions using our main asymptotics theorem. So here's an example. Say my function, n going from 0 to infinity, an divided by n factorial x to the n is equal to 1 over 1 minus sine x. So this is a generating function that has positive coefficients. It's a generating function that comes from a combinatorics problem. But let's just suppose we're handed this and like to know the approximate growth rate of an. So the first idea is to identify the singularities of this generating function. So the singularities are at pi over 2 plus any integer multiple of 2 pi. The smallest singularity, the singularity with smallest complex magnitude, is simply pi over 2. So this is the smallest singularity. And when we first introduced singularities, I did this as an example. I showed that multiplying by pi over 2 minus x does not remove the singularity in this example. You need to multiply by 2 factors. So we've seen in an earlier video that the limit as x goes to pi over 2 minus x squared divided by 1 minus sine x, this is actually equal to 2. So what I'm saying is you need 2 terms instead of just 1 to get this a finite constant. So therefore, remembering the main theorem, which I didn't copy down on this page again, but go back to the previous video if you'd like a refresher, the coefficient an divided by n factorial is asymptotic to this constant, 2, n to the alpha. In this case, the alpha that I used in the theorem is 2. So it would be n to the alpha minus 1 power, or 2 minus 1 power. It's alpha to the first power, divided by gamma of alpha, so gamma of 2. Gamma of 2 is 1. It's 1 factorial, so that's just 1. And then I multiply by this r value, pi over 2, to the n plus alpha power, so n plus 2 power. And so an is asymptotic to n factorial times 2n times 2 divided by pi to the n plus 2 power. And if you'd like, you can expand n factorial using Stirling's approximation, but I think this is good for now. So I'd like to end this sequence of examples with a non-example. So here's an example of when this approach will not work. So this approach that we've been introducing fails for a generating function like this one. So 1 over the square root of 1 minus x squared. We've actually gotten this generating function from our work with the exponential formula. This, if you recall, was the generating function for the permutations of n that have only even-sized cycles. So we've seen this example before. However, this approach will not work because I have singularities at both plus 1 and minus 1. Both of these singularities are equally close to 0. So the approach that I've introduced only works if there's a single singularity closest to 0, not if there are two. Now you can still write down analogs of the theorems that we've developed and adapt the procedures that we've seen for this situation. And if you look in the book Generating Functionality, there is some discussion about that procedure, but I'm not going to introduce it in this class because most of the time, all the generating functions we will see are amenable to the techniques I've introduced. And it's not worth proving a whole bunch more theorems just to include these special cases. So if you are interested, check out the book. But I'd like to point out that for this example, since I have two singularities that are different with the same complex magnitude, our approach will not work because if I try to remove the singularity at 1, say, then I do not get a convergent series on values larger than 1, which was what was needed in the proof. Okay, excellent.